Hello everyone, let's look at this series here. We have this series with n factorial in the denominator, and we also have n plus 2, that's that quantity that's raised to the n power. And so for this kind of series, we usually try to use the ratio test to test for its convergence. And so let's start writing down the terms that we need for the ratio test. So first, we need to write down the term that's so we are going to call this expression right here the an. So if we call this an, then we are going to get n plus 2 to the n power, and then that's over n factorial. Okay, now what about the a sub n plus 1? Then that's going to be replacing all the n's with the n plus 1. And so let me actually just highlight that here. And so we are getting n plus 1 right here. Oh, actually, so let me just use a different color to make it more obvious. So we have n plus 1 right here. And what happens is that we are going to get n plus 1 and then plus 2 to the n plus 1. And then all over, it will be n plus 1 factorial. Okay. And if we simplify this, then we are going to get n plus 3 to the n times n plus 3 to the first power. And then in the denominator, we are going to get n plus 1 times n factorial. And then you may say, why do I put it in this form? You will see when we do the ratio test. When we take the ratio of the a sub n plus 1 over the a sub n, then we are going to be canceling a lot of the factors. So if if we see this n plus 1 factorial, it's better to write it as n plus 1 and then times n factorial. So you can see that they have the same factor n factorial in there. So there are a lot of things that will get canceled. So now let's start doing the ratio test. So when we do the ratio test, we are going to take the limit as n approaches infinity. And then the absolute value of, we have the a sub n plus 1 over the a sub n. And then in this case, we are going to just treat it as a multiplication by multiplying by the reciprocal of this a sub n, because that's dividing by a sub n, right? So we can multiply it, we can multiply with the n factorial on top and then the n plus 2 to the n power in the bottom. Okay, so that would be the absolute value of, now we are going to just write this expression right here. That's the a sub n plus 1. So we have the n plus 3 to the n power, and then n plus 3. And then we are having, what is that? That's n plus 1 then times n factorial. And then now let's take the reciprocal of this one. So we are going to get n factorial over n plus 2 to the n power. And then we take the absolute value of that. Now see that since all the factors are positive, so in the next step, we can remove this pair of absolute value. We don't need the absolute value symbols anymore. And then as you can see here, we can cancel out this n factorial and this n factorial. So let's do that. We can cancel out the n factorial. Then we are going to get the limit as n approaches infinity. We are having, what is that? That's n plus 3 times n plus 3 to the n power. I actually just switched the two factors. And then we have n plus 1 in the denominator. and then we have the n plus 2 to the n power. So we have the n plus 2 to the n power. Okay. So now when we consider this limit right here, we can actually put this n plus 3 and then n plus 2 together because they both have the same exponent, right? So we can actually just put it like this. So we are getting n plus 3 and then over the n plus 1 times. And then now I'm going to put those two factors under the same exponent. So we are going to get n plus 3 and then n plus 2. And then all that is raised to the n power. So now we have a product. And so let's do a quick check here. We know that as n approaches infinity, then n plus 3 over n plus 1, this quotient is going to be approaching 1. This fraction is approaching 1. We actually need to check whether the limit for this factor exists before we can actually take the limit for each individual factors. So let's just put the problem aside, and then we want to check this one first. And so how do we check? We can just do it on the side right here. We are going to, let me see. So we are going to get, so let's do it here. So n approaching infinity, and then we have n plus 3 over n plus 2 to the n power. And so for this one, we need to figure out whether the limit exists, or if it exists, it equals what, right? So first, we are going to let y be equal to this function, n plus 2 to the n power, okay? And then we are going to do the natural log on both sides of the y, right? So we get ln of y. That's equal to the ln of this expression right here. So we have that. And then so you know that we can bring this exponent to the front, right? So we are going to get ln of y is equal to n times ln of n plus 3 over n plus 2. So in this case, we are going to rewrite it so that we have an indeterminate form. So we are going to get ln of n plus 3 over n plus 2, and then divided by 1 over n. And so why do we do this? Because we know that we are going to take the limit as n approaches infinity. So in this case, when we let n approach infinity, this quotient right here is approaching 1. So ln of 1 is going to be what? It's going to be approaching 0. What about the bottom? When n approaches infinity, 1 over n is also approaching 0. So we are actually getting an indeterminate form here. So in this case, we are going to, when we take the limit, we can apply L'Hopital's rule. So let's apply the limit here. So when we apply the limit as n approaches infinity for the ln of y, right? We are going to have the limit of this, but then we can apply L'Hopital's rule at the same time, right? So let's take the derivative of the numerator and the denominator separately and see what's going on. So if we are doing that, then we are going to get what? The derivative, it's going to be n plus 2 over n plus 3 times. No, I think I need more space for that. So let me write my 1 over n like this. And then I'm going to get a longer fraction right here, which is n plus 2 minus n plus 3 all over n plus 2 square. And then all that is over All that is over negative 1 over n squared. Now, due to the space, I'm not going to show the work for simplifying with this expression right here, but eventually we are going to actually just get to we're actually just going to get to, let me see what that is. So we're just going to get to this expression right here, which is n squared. Yeah, so let me rewrite that a different way. So negative 1 over n squared. So we are going to get n squared over n plus 3, and then n plus 2. And so you know that this is actually just equal to 1. So see what's going on here. I think we may need more space. So let me just move this up slightly so that it's not going to, yeah. And then right here, I think the n is missing, right? So let's go back and then put that n back. I think I accidentally moved it. So we actually figure out that the limit for L1 of y is equal to 1. But we actually want the limit of this thing, the y, right? So in this case, the y is actually, what is that? So y is actually just equal to e to the first power, which is this one right here, right? So we're just going to put that here. So as you can see, that's actually being put here. So y is equal to e. And so the limit of this factor exists and the limit of this factor exists. So that means we can use the limit laws to separate this. So we are going to get what? We are going to get the limit as n plus 3 over n plus 1. And then times the limit of this n plus 3 over n plus 2 and then raised to the n power. And then so you know that this first one right here is approaching 1. And then what about the second one right here? The second one is it's given by this e, right? So it's actually just equal to e there. Yeah, so I should just tell you that, okay, so this is actually giving you this one. Okay, so what is the answer? The answer will just be e. Now, e it's greater than 1, right, as you can see. Since e is greater than 1 by the ratio test, this series diverges. And so now we can write down the conclusion. So by the ratio test, the series n plus 2 to the n over n factorial, and then diverges. And so let me just highlight this final answer right here. Okay, so that's that. Okay, so that feels like a long problem, and in fact, it is a long problem. It's a lot of work, right? Because we need to put the problem aside when we get to this step here, and then figure out whether that limit exists, and if it exists, what that limit is equal to. Okay, so that's it for this problem. If you like this video, please subscribe to my channel and then give me some support. And thank you for watching this video. I will see you next time.